All right, let's discuss how to find the variance for the least squares estimators. So just as a reminder, our least squares estimators are b naught equals y bar minus b1 times x bar, and b1 equals sxy divided by sxx, which this is the same thing. That is just basically notation for the sum from I equals 1 to n of xi minus x bar times yi minus y bar divided by the sum from I equals 1 to n of xi minus x bar squared. Right? And if we were to distribute this, these guys, we could easily show that this is the same thing as from I equals 1 to n of x sub I minus x bar times yi divided by the sum from I equals 1 to n of x sub I minus x bar squared. Okay, and I think I showed this, this relationship here in a previous video, but it's relatively easy to show. If you were to distribute, you would find that this is true. If you have questions about that, you can comment about it in the comments for this video. Okay, so we need to find the variance of these two estimators, b naught and b1. It makes sense for us to start with the variance of b1 since b naught depends on b1. I think it's really important whenever you're using an assumption to be clear about what assumptions you are using and when you're using them. So let's go ahead and write out what assumptions we're going to need to figure out these variances. The first assumption is that we will need the homogeneous variance assumption, right? Okay, and what this says is that the variance of our error term equals sigma squared for all I equals 1 to n, which basically is saying that there's a constant variance regardless of which observation we're looking at. Remember that yi equals beta naught plus beta 1 xi plus the error term. So beta 1 and beta naught and xi, they're all non-random. So when I take the variance of yi, it's going to be the same as the variance of that error term, which is sigma squared. Okay. Another assumption that we need to use is the uncorrelated variances. So uncorrelated error term. Okay. And so that is basically that the covariance of our error term for two different observations is going to equal 0 as long as I doesn't equal j. Okay. And the last but not least is we need that xi's are non-random. Okay. So I'm not concerned with the variability in xi. It's treated like a constant, basically. All right, using these three assumptions, let us start by finding the variance of b1. Okay. So the variance of b1, this is the same thing as saying, we'll go ahead and find the variance of sxy divided by sxx. Okay, and remember your properties of variance. Okay, so say I want to know the variance of a times x. This is a squared times the variance of x. If a is a constant and x is a random variable, this is by definition, right? This is a property of variance. So let's go ahead and use that property. And let's pull out our constant. Our constant is the denominator since it doesn't depend on y. X is treated like a constant. Okay, when you pull it out, you're going to need to square it. All right, so now let's go ahead and write this out. What is Sxy? It is the sum from I equals 1 to n of xi minus x bar times yi minus y bar, which, like I said previously, that's the same thing as saying just times yi, right? And you can show that mathematically that's the same thing. Okay? So remember, when you break out a variance of a sum, so let me write this as a little sidebar. So the variance of ax plus by. All right, this is just a sum where a and b are constants. This is equal to a squared times the variance of x plus b squared times the variance of y plus 2 times a, b, the covariance of x, y. Okay, so this is a property of variance of a sum. Okay, so when I think about putting this variance in, right, this is a constant, right? This x minus x bar is basically a constant. Right? Now, the covariance of different y's, this covariance term basically at the end here, I don't have to worry about it because I have that assumption that basically the covariance of one observation and another observation equals 0, right? That's my assumption. That's from my assumption. Okay, so this is equal to 1 over Sx x squared times, I can pull out this sum, right? When I pull it out, it becomes squared, right? This xi minus x bar becomes squared times the variance of yi, right? And I don't have to worry about the covariance because of this assumption. Okay, so this equals 1 over Sxx, right? Instead of writing it as, let me write it Sxx squared, right? This is the same thing. Okay, now notice this is Sxx, right? This, we've already discussed, is sigma. It doesn't depend on I, sigma squared, sorry. And it doesn't depend on I due to our homogeneous variance assumption, right? So this is also an assumption. Okay? This other piece is Sxx. So we notice that one of the Sxx's will cancel because one's in the numerator, one is in the denominator. And I'm left with sigma squared, and then I still have one Sxx on the bottom. Okay, so there we have it. That's my variance of B1. Okay, so now let's find the variance of B naught. So the variance of B naught, and recall that B naught is y bar minus B1 times x bar. Okay, and we know that y bar is random, right? The mean of y is random because y is random. What is B1? Let's just quickly recall what's B1. So B1 is Sxy divided by Sxx. Since it involves y, right? The numerator involves y. This is the sum of x sub I minus x bar times yi divided by the sum of x sub I minus x bar. squared. And the numerator involves y, so b1 is random. Okay, so since it's random, I need to, when I'm calculating this variance, I need to calculate the variance of b1. I need to consider that. Also, when I'm bringing this variance basically into the sum, I need to remember how to do that. So I wrote it up above, but I'm just going to write it one more time. So the variance of some constant times a random variable plus another constant times another random variable is equal to the constant squared times the variance of the first variable plus the constant squared times the variance of the second variable plus 2 times the constants and the covariance of the two variables. All right, we're going to need that for sure as we calculate this guy. So let's go ahead and distribute that variance. So I end up with the variance. Now, there's no constant in front of y bar, so that's just the variance of y bar. All right. Then the constant in front of b1 is basically x bar. So that's going to get pulled out. And the negative sign, basically, once it gets squared, it's positive. Okay. So times the variance of b1. All right. Now I need to be considerate of the covariance, okay? Plus 2 times the constant in front of y bar is 1. The constant in front of b1 is x bar. Covariance of y bar, b1. Right? This covariance, it turns out that it is 0, but that doesn't follow directly from our assumptions. It needs to be shown. Okay? So unlike in previously, it followed directly from our assumption that I didn't need to worry about that covariance. Here, we do need to kind of figure out what that covariance is. We can't just assume it's 0. There's some math that goes behind why it's 0. Okay, so before we move on, I'm going to figure out this covariance. All right, the covariance between y bar and b1. And actually, before I do that, let's talk about what is y bar. Okay, so y bar is the sum from I equals 1 to n of x sub or y sub I divided by n, right, by definition. All right, and I'm going to use the centered model because it helps us here in our calculations. So this is y sub I is the same thing as beta naught star, right? Remember the centered model uses the star plus beta 1 x sub I minus x bar, so the model is being centered, plus epsilon sub I. Okay, which I'll provide a link in the comments to this video. It talks about the centered model, but this is what yi is in the centered model. Okay, all this divided by n. The reason that the centered model is really nice, so this is going to be equal to, when I distribute this sum, right, because I'm summing each of these guys, I'm going to have the first term, I'll have n beta naught, since that doesn't involve I, okay, plus beta 1 times the sum from I equals 1 to n of x sub I minus x bar, okay, plus the sum from I equals 1 to n of epsilon sub I, okay, and all that's being divided by n. And this is why the centered model is really nice, because we know that this sum here, it equals 0, okay? You can go ahead and distribute that sum, and it's relatively easy to show that this equals 0. Okay, so y bar equals n times beta naught plus the sum from I equals 1 to n of epsilon sub I. All right, and then I can distribute this divided by n. So this is divided by n, and this is divided by n. Okay, so these guys cancel here, and I'm left with beta naught star plus epsilon bar, right, or the mean of our error terms. Okay. Okay, so that's what y bar is, and I kind of want to do some similar type derivation for figuring out what is B1. Okay, remember B1, we know it is the, well, we know it is SXY divided by SXX. Okay, and this is the same thing as the sum from I equals 1 to n of x sub I minus x bar times y sub I. I'm just actually going to leave that as SXX. Okay. All right, so let's go ahead and once again, let's plug in the centered model for y. All right, it's going to make our calculations easier. So let's do that. All right, so I have yi is beta naught star plus beta 1 x sub I minus x bar plus epsilon sub I. Okay, all this divided by SXX. All right, so now I can simplify this by multiplying each of these terms by x sub I minus x bar. So the first term, the second term, and then that error term. Okay, so let's go ahead and do that. Let's distribute this. So this equals the sum from I equals 1 to n, okay, of x sub I minus x bar times the first, what do I have, beta naught star, right? Plus this sum again, so I'm distributing the sum as well, okay, times beta 1 x sub I minus x bar. All right, and then lastly, once again, another sum. I'm gonna need another line here. I ran out of space. Okay, x sub I minus x bar times, this last one is just epsilon sub I. Okay, and then all of this, of course, is still being divided by SXX. All right, and now some things simplify, so let's look at this carefully. This first term here, the beta naught, basically it can go out front because it doesn't involve I, and when it does, we do notice that this is the sum here. We know that that is 0, so that's 0 and basically goes away. Okay, 0 times beta naught is just 0. All right, the second piece here, we have 2x sub I minus x bars, so that's basically, let me go ahead and write this so I can pull out the beta 1, okay, and this becomes x sub I minus x bar squared, which is SXX, okay, and I'll write it like that in the next step. Then I have plus this error term in the back. Can't really simplify this one right yet. Okay, all right, so what do I have here? This equals beta 1 SXX plus, okay, this difference divided by SXX divided by SXX. These guys cancel. Okay, so I'm left with, this is beta 1 plus all right, divided by SXX. All right, so this is what B1 equals. All right, took us a long time to get there, but trust me, it was worth it. So this is what Y bar is, and this is what B1 is. So now when I want to figure out, well, what's the covariance between Y bar and B1, I can say, oh, well, that's the same thing as the covariance between, if I scroll up, Y bar is this guy, so B naught star plus epsilon bar. So B naught star plus epsilon bar, okay? And then B1 is the same thing as B1 or beta 1 plus this sum divided by SXX. Okay. All right. So now I need to figure out what is this covariance. Okay, side note, in case you've forgotten how to calculate a covariance. So like covariance of two different random variables, say A and B. This is equal to the expected value of A times B minus the expected value of A times the expected value of B. Okay? So we need to use that. So this covariance of y bar minus b1, okay, this is going to equal the expected value of this product. Okay, so multiply this guy times b1 plus this sum. Okay, minus the expected value of beta naught star plus epsilon bar times the expected value of beta 1 plus this sum. Okay. Okay. So let me try to do some color coding here. So we need to know the expected value of this product. Okay, so let's start with that. To figure out the expected value of this product, it's going to help a lot if I distribute. So, you know, multiply this by this guy, and this by this guy. Let me use two different colors. So this one by everything, and then this one by everything. So let's go ahead and do that. So this equals the expected value of beta naught star times, I'm going to go ahead and just multiply it by each piece, times beta 1 plus beta naught star times this sum from I equals 1 to n of x sub I minus x bar divided by sxx times epsilon sub I. So what I've done is I've multiplied beta naught star by each piece here. Okay. Then let's do the same thing with epsilon. So epsilon bar, let's do the same thing with epsilon bar. So then plus epsilon bar times beta 1, and then plus epsilon bar times that sum from I equals 1 to n of x sub I minus x bar epsilon sub I divided by sxx. Okay, so this is the first, this is the product, and then minus. Now, this, we can figure out this expected value here. Beta naught star is a constant, so the expected value of it is just itself. Epsilon bar, okay, is the sum of all of our epsilons divided by n, and we know the expected value of epsilon is 0, so when you sum them all up and divide it by n, you should just get 0, right? So this becomes minus beta naught star times, or plus 0, okay, that's what that expected value is, times, okay, this back piece here, we can figure out this expected value, the expected value of beta 1. Beta 1 is just a constant, so it's just a number. There it is, beta 1. You just leave it, the expected value of it itself. And then plus, once again, this is a sum that involves a multiplication by epsilon. And when you take the expected value of epsilon, you get 0. So this is just 0. All right, so now moving back to this top piece here, I can find the expected value of each piece of the sum. So I have this equals this first piece of the sum. These are just constants, so their expected value is just themselves. Okay. The second piece of the sum, I have this epsilon I term, right? I have this epsilon I term, and when I take the expected value of epsilon I get 0. So it basically becomes whatever this front material is, it's a constant, times 0, which is just 0. So this is plus 0. This piece here, once again, I have the expected value of epsilon bar, which again is going to just be 0 because it's the sum of a bunch of zeros divided by n. So this is going to be beta 1 times 0, which is just 0. Okay, and then lastly, this last piece, I have the, actually let me write down this last piece though because it's a little more complicated. I have the expected value, well, let me pull out my constants. So from I equals 1 to n of x sub I minus x bar divided by sxx, the expected value of 1 over n times the sum of epsilon sub i's, right? This is what epsilon bar is, times epsilon sub I, right? And you can show that because the covariance is 0 and the expected value is 0, that this is also 0. Okay, and I'll leave that as an exercise for you to do. But this equals 0. Okay, once again, it's because the covariance is 0 and because the expected values are 0. Okay, so because that is 0, then this whole piece here zeroes out. And don't forget, we still have at the back, we have this minus beta naught star times beta 1, right, plus 0 times beta 1 plus 0, so that goes away. Okay. So what am I left with right now? Looks like I still have on the table, I have beta naught star times beta 1, right? And I have a ton of zeros, it's all zeros. And then I have left at the back minus beta naught star times beta 1. And that is how I finally get my final conclusion that this is 0, right? So the covariance between y bar and b1 is 0. All right, so once you believe that the covariance between y bar and b1 is 0, then we can go back to figuring out what's our variance of b naught. All right, our variance of b naught, b1 times x bar. All right, so this is going to be the variance of y bar plus x bar squared times the variance of b1, right? Don't need to worry about my covariance because I've shown that the covariance between b1 and at y bar is 0. All right, so then this is equal to the variance of 1 over n times the sum of yi, that's what y bar is, plus x bar. Now I figured out what the variance of b1 is already. It's sigma squared over sxx. Okay, 1 over n squared when you pull it out times the sum from y equals 1 to n of the variance of yi. All right, the error terms are uncorrelated, so I don't have to worry about the covariance here, right? So that's just like the sum of the variances. That's all I have to write. I don't have to worry about any covariance. Covariances are 0. All right. Now this variance here, we know that this variance is sigma. So this equals 1 over n squared. I'm just going to distribute that square. So then the sum from I equals 1 to n of sigma squared plus x bar, sigma squared all over sxx. All right, and this is basically n of the same thing. There's no I here, right? So this basically, that's 1 over n squared times n sigma squared, right? Plus x bar, sigma squared all over sxx. All right, so this n cancels with one of those n's, and we can also pull out a sigma squared. So let's do that. we are left with our final answer of sigma squared times 1 over n plus x bar over sxx. This is the variance of B naught.